Okay, in this chapter we're going to be covering in particular stoichiometry, a very critical concept. If you have a good handle on conversions, it's really easy to do. We're just getting our conversion factors from a balanced chemical equation to relate the reactants from products. So to begin, let's look at basic chemical reactions and what they show us, and we'll introduce conservation of mass. This is a typical chemical reaction. Our reactants are listed on the left side, products on the right, since we read left to right. Reactants to products, always written this way. Keep in mind when we have a chemical formula, that's showing us the formula for a given molecule. It's always good to visualize. When we have two of something, this is two nitric acid molecules, this means that we have two molecules that are being produced in this case. So keep in mind that's not part of the formula. It's just saying we have two of that atom or molecule or ion, whatever it's showing. And as we'll cover a little bit as we go along, we always use arrows to show the direction of the reaction. They always go left to right. There are cases where they go left to right and right to left. That's more advanced chemistry, but you do have reactions that go both directions, but they always go at least from left to right. And last but not least, we'll mention in a minute the phases after, in this case, after N2O5, after water, shows what phase they're in, whether liquid, gas, aqueous. We'll discuss these as we go along. So a chemical equation describes really the proportions of reactants and products in a particular chemical reaction. It relates numbers to numbers. Numbers of reactants to other numbers of reactants, or numbers of reactants to products. And we tend to think about that in terms of moles. Moles still just another measurement of number. And so it describes changes really on the atomic or molecular level. We have bonds being formed and broken. We have compounds changing phases. We have physical states of reactions that we need to include. So we have something happening in a given process. Physical states listed at the bottom. This is, as I mentioned, after the compound, we often give more information about a reaction and describe what phases these different components are in. Solid, liquid, gas, aqueous is slightly different. We'll discuss that in a second. I do want to mention you often find more information listed than just what's shown in these reactions here. You might have, in this case, plus energy. If I can write it with this pen. You get energy produced or energy absorbed. Above or below the arrow, you might see more information. Sometimes don't let that confuse you. It often is used to show reaction conditions, the temperature, the pressure, if there's a catalyst. So we can get lots of information from a chemical reaction. We won't deal with all that detail right now, but you should be aware that there's a lot of information that can be presented and often is presented in a chemical reaction, in addition to just the reactants and the products. So the basic states of substances, the phases or the states of matter, are shown, as we discussed, by abbreviation in parentheses after each compound or each chemical. So for water, this shows solid, liquid, or gas. Those are the basic phases you're aware of. So obviously solid, liquid, gas are the main phases. Aqueous is not the same as liquid. People get that confused all the time. It means dissolved in water. If you take sodium chloride, if you take a salt crystal, take table salt from your salt shaker, pour that into a glass of water, let it dissolve, you have not turned that solid sodium chloride into a liquid. That would take, you have to get up to 2,000 degrees centigrade or so to actually get it to change phases. You've dissolved it, so you've actually formed a mixture of sodium chloride and water. So that's different than turning it into a liquid. Up arrows and down arrows are usually used for aqueous phases for products. Basically an up arrow, if you think about what happens if you have a glass, have a beaker of a reaction, you put something in there, you have a reaction that produces a gas phase product. It produces bubbles, the bubbles rise to the top, and that's what the up arrow is indicating. It's a kind of a lazy way of saying gas is produced. Like when you have a soda, you let it sit there, the CO2 eventually turns into gas. It's being, leaving the bottle itself of soda that you're drinking and turning into gas phase. So it's rising up to the top. So simple enough. And the down arrow, by the same token, if you have reactions that are producing a precipitate that are producing a solid, then the solid ends up settling to the bottom of the beaker eventually. So that's often called a precipitate or a solid that's being produced. Again, it's kind of a quick and dirty way of showing that a solid is produced instead of just saying S. Not a big deal, not really that much easier, but it's a common notation that you do need to be aware of. So we want to mention first a few different types of reactions to be aware of, and later you can predict reactants and products by understanding what the basic types of reactions are. The first is a synthesis reaction, and really you're taking two elements and combining them to form a more complex molecule. In this case, we're taking nitrogen, molecular hydrogen, and they're combining to form ammonia. Now there are other products that nitrogen and hydrogen can combine to form, so in this case you will not know necessarily what the product is without being told. Decomposition is just the reverse of this process. Typically decomposition is a compound decomposing into its base elements. You can have partial decomposition, in which case compounds may decompose into simpler compounds. By the same token, you can have synthesis, in which case you don't start with elements, you can actually start from other compounds and combine them to synthesize a more complex molecule. But we tend to think about going from base elements to compounds or compounds to base elements for synthesis and decomposition reactions. There are also two different types of reactions that's good to be aware of: single replacement or double replacement. Some texts refer to these as single displacement and double displacement. These typically occur with ionic compounds, where we actually have well, for single replacement, you have an ionic compound, and one of the ions is being replaced by another ion. So in this case, we have sodium bromide and reacting with elemental iodine and producing sodium iodide and bromine. Now, this is a case where we could predict the products, and we'll do a few examples of that in a bit. All right, so with sodium bromide, if you just had these two reactants and we're trying to decide what is going to be formed, well, we look at what type of ion will the iodine form. We know the iodine normally forms a negative one or an anion, so that means it's going to replace the bromine ion, or the bromide ion, I should say, to be proper, and so we get sodium bromide form. And of course, in this case, we have a compound and an element, so we'll end up producing a compound and an element. Of course, bromine in its elemental state is one of the diatomic elements, so it's Br2. And when iodine forms an ion, remember that the element is I2, but the ion is just I with the -1 charge. So you don't carry the 2 over into the compound. We take the ions, figure out the formulas for the compound, and then we actually balance equations, which we'll get to in the next section. Double replacement reactions. Basically, we're taking two ionic compounds and the cations are switching places. Well, or the anions. This ends up being the same thing effectively. In this case, potassium nitrate and calcium hydroxide. Well, the potassium ion is taking the place of the calcium ion. They're switching places. But when they do this, we need to make sure the charges of each compound balance. So potassium has a +1 charge, so when it forms potassium hydroxide, we have 1 potassium for every 1 hydroxide. Calcium is taking place of potassium, so we get calcium nitrate. Now in this case, calcium, of course, has a +2 charge, nitrate -1, so we have to have a calcium nitrate, 2 nitrates for every 1 calcium. So we switch to ions, and then we actually balance out the formula to make sure that the overall compound is neutral. And then later we get to balancing the overall equation using coefficients. And this is showing the basic process. As we said, synthesis, you have sort of visualized it a little bit better. Two different elements or compounds combined to form a more complex molecule or compound. Could be ionic compounds too. Decomposition, you're separating or splitting apart a compound into its base elements, typically. Single replacement, an element is replacing one of the components of an ionic compound. Again, it could be the cation or the anion. We don't know which. So you have to look at the element itself to determine which ion is it going to replace. And double replacement, in this case, the cation switch places, again, or you could look at it as if the anion switch places. Same thing effectively. And one other type of reaction we need to look at. Combustion reactions. This is in the next section in this text, but I think it's good just to include them here for completion. Really all we're going to say about them right now, but you should understand the differences between complete and incomplete combustion. Complete combustion is just you have fuel and oxygen produce water and CO2. Fuel, in this case, a hydrocarbon, typically, get back there, CH4, reacts with oxygen to produce water and carbon dioxide. Incomplete combustion, The exact same thing, except instead of producing carbon monoxide, instead of producing carbon dioxide, we produce carbon monoxide. And the reason it's called complete combustion is we're getting really as much energy out of this reaction as we can. For many reactions, imagine that, well, chemicals react to get to more stable configurations in most cases. There's some other chemistry we'll discuss in 1 to 5 and 6, but they're trying to go from high potential states to lower potential states. And so whenever you get water and CO2 produced, these two molecules are actually very stable. They don't have much potential energy. So we're actually taking all the energy that's contained in these reactants, and it's being released as heat and light, and we're getting two very stable molecules being produced. Now, for incomplete combustion, carbon monoxide is still a fairly reactive chemical. It actually still can be burned. It contains chemical potential energy. So it's called incomplete combustion because there's still some potential for burning. If you take carbon monoxide and have the right concentrations, react it with oxygen, add a spark to it, it will ignite and burn. So we get more energy out of it. So that's why it's called incomplete combustion, because it still contains some useful energy. The law of conservation of mass, this leads to, most of you know about balancing chemical equations. We balance chemical equations because we cannot gain or lose any matter. We're not dealing with nuclear reactions here, just chemical reactions. So we end up with the same mass that we start with. So that's what this is stating. The sum of all the masses of the reactants has to equal the sum of all the masses of the products. So we don't gain or lose any matter. And stoichiometry, which is what this chapter is focusing on, is quantifying that measurement, quantifying the relationships between the reactants and the products. We can use this to predict how much of each reaction we need to produce a certain amount of product, how much product we expect to be produced, and understanding energy being absorbed and released also for these processes. So, and the stoichiometry is really relating to the coefficients in a balanced chemical equation. This is what makes sure that our overall reaction is balanced, that we're conserving mass. And this is showing a balanced chemical equation. You have the reactants, products, and again, the coefficient is the number in front of each compound or element. Coefficients only go in front, not in the middle. People try to get stuck on balancing, try to squeeze them in the middle of a compound for some reason. Once you write down the formula for a compound, don't change that formula. We just use coefficients in front. And in these two cases, the 1 is implied. We don't need the 1. It's like subscripts in chemical formulas. You don't need to put the 1 in. It's implied. So anything not being shown usually is going to be a 1. And so what this shows us is that for every, in this case, for every iron 3 oxide, we need 3 sulfuric acids because it's a 1-to-3 ratio. And that means for every 3 sulfuric acids, we'll produce 3 water molecules. And we'll produce 1 iron 3 sulfate. So we can relate numbers of each compound to each other. And by the same token, we can relate moles of each compound. That's what we really care about because we can't react 1 molecule or 1 formula unit at a time. But we can relate moles of each one. So for every, back up here, for every 1 mole of iron 3 oxide, we need 3 moles of sulfuric acid. And again, in 104, you haven't covered naming sulfuric acid yet. You can call this hydrogen sulfate. That'll be fine for right now. But it just shows this ratio of numbers to numbers. So it's either numbers on the molecular scale or on the macro scale where we really relate moles to moles.